So we have the integral going from 1 to infinity. So if we're able to prove that this thing converges, we're going to take the derivative the way, take the antiderivative the way we normally would. So let's see if we can definitively prove if it converges or not. So do you guys remember how to tell if it converges? It's all right if you don't. I don't think we covered that much of it on Tuesday, so it would be a good idea for us to review a little bit. So one of you gave a really great example of convergence when we had class a few days ago. You described it as things coming together, which is a really, really great definition. So convergence of an infinite series or convergence of an integral occurs when we approach a certain value. Then likewise, divergence occurs when it looks like we don't really approach a certain value at all. That would be divergence. Convergence and divergence are opposites. So let's give some examples of convergent functions. I'm going to do my best to draw. I really like natural log of x. That's a pretty good example for what I'm trying to illustrate here. So natural log of x keeps increasing without bound. There is no horizontal asymptote. It doesn't get infinitely close to a value. It doesn't really approach a certain value. So that's the most basic definition of convergence. For a function to be considered convergent, it has to approach a certain value. And if we were to maybe go on our calculators and trace the graph of natural log of x, or maybe if we made some kind of xy table, we would see that the y just keeps increasing on and on without bound. The y value does not approach a specific value, so we can tell that natural log of x does not converge. Natural log of x diverges. Now let's talk about a different function. Let's talk about the basic rational function, 1 over x. So we know what it looks like. Something kind of like this, where it has a vertical asymptote, it has a horizontal asymptote, and they both coincide with our axes. The vertical asymptote is going to be the y-axis. Our horizontal asymptote is going to be the x-axis. And we have some kind of a symmetry going on here. We have symmetry about the line y equals negative x, which means we have some image of this pre-image occurring in the opposite quadrant, in quadrant 3. So we want to discuss if this converges or not. So let's talk about what happens as x gets increasingly large. So if we take more higher and higher and higher x values, let's see if we can tell if y approaches a certain value. So for this one, same thing applies. We could graph it and then analyze the graph, maybe just using Wolfram Alpha or Desmos, or maybe just one of your TI graphing calculators. Tracing the graph will tell you if it approaches a certain value, but we can also try an XY table for this one. So obviously 0 won't work. That would result in 1 over 0. So we're going to start with a 1. So then let's say if we plug in a 1, we're going to get just 1. Let's say we plug in 10. 1/10, plug in a 100, we get 100. Let's skip a few. Let's say we plug in a million. We get 1 over a million. Oops, I wonder who wrote that. Oh wait, I did. So we have a million, and then the y value to go along with that would be 1 over a million. So we can tell that as x gets larger and larger and larger, y is going to get smaller and smaller and smaller. So theoretically, if x were to reach infinity, y would have to reach 0. So this one definitely converges because we do approach the value of 0. So I want to ask you guys a few questions about convergence and divergence. It's really important for us to understand these two things, because the third main idea of this particular calculus class would be the study of infinite series and infinite sequences. And convergence and divergence are so very important to fully understand what those things are. So I want to maybe just write some functions on the screen, and I want to hear from both of you guys in the chat. So tell me if this function converges or if it diverges in the chat. We want to just see if this approaches a certain value as x approaches infinity. So I guess the formal definition of convergence would be if this limit exists. If the limit exists, then our function converges. If the limit does not exist, the function does not converge. So just take a few minutes. If you want to take a look at the graph of sine of x, or if you want to make an xy table and see if it converges, go right ahead. Pick whichever method you're the most comfortable with. And I would like to hear from both of you in the chat whether you think sine of x converges or if it diverges. What do you guys think? I want to give you guys a few different examples to try. Oh, and for each of the answers, make sure you put the letter number along with the answer so we know which function we're talking about. So let's just do these four. So I would like 4 answers from each of you guys, whether or not each of these functions converge. And like I said, please put the number, or please put the letter of whatever problem your answer pertains to. And of course, we will be going over these as a group. So don't worry if you're not too sure. I want you to at least guess if you're not too sure if one of these converges or diverges. We will be going over them together, though. So I've received one answer. Thank you for that. So keep going. And of course, let me know if you have questions about anything. So let's go over these real quick. So our first function we have is sine of x. So how do we know if sine of x converges or not? So we know it converges if the limit exists and if it looks like it approaches a certain particular value. So sine of x, we know what that looks like. We know it just keeps oscillating back and forth between 1 and -1. Doesn't really approach a certain value. It doesn't really look like it converges at all, because we know for it to converge, it has to get closer and closer to a particular value, and this one does not. If we were to take the amplitude at any of these locations, the amplitude would stay the same forever and ever and ever. We would not approach a certain value, so sine of x diverges. And now let's talk about square root of x. So we note that as we keep increasing our domain, if we keep making x get larger and larger and larger, we can tell that the range is going to get larger and larger and larger as well. And it doesn't really have a particular endpoint. It just keeps increasing without bound. It doesn't really approach a particular value. So this one also diverges. And then this one, to tell if this limit exists, we can either use L'Hopital's rule, or we can maybe use some of our tricks from pre-calc and algebra to maybe just factor this real quick. So if we were to factor this, we would get x minus 2 times x minus 5 upstairs. And then downstairs, we have x minus 2. So the x minus 2 on top cancels with the x minus 2 on the bottom, leaving us with x minus 5. So the real question is, does x minus 5 converge? Let's take the limit. Limit as x approaches infinity of x minus 5. So we have infinity minus 5. It doesn't make infinity any less. This -5 really doesn't have any effect whatsoever, so this limit does not exist, so, which means that this converges. Or sorry, it means it does not converge. Diverges. And now for this one. So we know what e to the x looks like. This is e to the x. So let's turn this into e to the negative x by transforming not the entire function negative. We're not going to be changing the entire thing negative like that. We're only going to be making the argument of the function, aka the input. The argument and the input are the same thing. We're going to make the argument of the function negative. And what that does algebraically is it reverses the graph. It reflects it across the y-axis. So this right here is the new one that we have. And if we're to continue taking larger and larger values of x, if we had maybe e to the -10, e to the -100, e to the -1,000,000, e to the -billion, and so on, we could tell that this would eventually reach 0 if x were to approach infinity. So this one definitely converges. Very nice. Nice job, you guys. So let's continue. Let's see if we can evaluate this improper integral going from 1 to infinity of 1 over 1 plus x times dx. So first we want to see if the limit exists, because if the limit exists, it converges. If the limit does not exist, it diverges. So the difference between what we're doing now and the very last thing we did, telling if those functions converge, is we're taking the integral this time. In the last 4 functions, we didn't have to integrate. We simply had to tell if they converge or diverge, but we have an integral this time. So there is a very special condition that has to be met in addition to all of those for this to be integrable, for us to be able to take the integral of it. We're going to have to we have to determine if it converges to 0. So if we're only talking about a function or a series, if we're only talking about the function or a sequence, it can converge to any value. But if we're talking about an integral, it must converge to 0. It can't converge to anything but 0. So let's see if this converges to 0. So 1 plus 1 over x, limit as x approaches infinity of 1 plus 1 over x. So we could just imagine x getting larger and larger and larger. So I actually maybe want to reverse the order of these. So we have x plus 1 downstairs. So if we plug in a 10, we're going to have 1 over 11. If we plug in a 100, we're going to have 1 over 101. If we plug in a million, we're going to have 1 over 1,000,001. So the higher x gets, the less important this becomes. The less important this becomes as well. As x gets larger and larger and larger, this thing definitely approaches 0. So the limit does exist. It equals 0. So we know that we are able to take the integral. Not only does it converge, but it converges to 0. And that's the most important thing to consider when we're trying to decide if we're actually able to integrate something like this. So we have been given the metaphoric green light to go ahead and integrate this thing. Well, it looks like we have maybe a bit of a u substitution problem. We have u equals 1 plus x, and we have du equals dx. We have the integral going from 1 to infinity. And then this would be dx is going to be the same thing as du all over u. So let's integrate. The integral of 1 over u is natural log of u. Going from 1 to infinity. So it's important to note that we can't evaluate a function at infinity. So we're going to have to set it up as a limit. So we're going to take the limit as alpha goes to infinity. And we're going from 1 all the way up to alpha. So let's go ahead and put the function back in. We have 1 plus x. So we have limit as alpha approaches infinity of the natural log of 1 plus x. And we don't even really need absolute value bars anymore because we know that we're only dealing with positive values of x. And all positive values of x are going to return positive values of u. So we don't even really need the absolute value bars. Parentheses will work just fine. So then we have this going from 1 all the way up to alpha. So let's imagine we plug this in. So we're going to get natural log of 1 plus alpha. So as this goes on and on and on to infinity, this one actually diverges. Sometimes we have to go forward and do the integral to tell if it does or not. And the way we know that is because we have, if we were to just take the values of x, if we were to take larger and larger and larger values of x, this would just get increasingly large. Whatever we have inside the parentheses, this would tend towards infinity. And we know natural log of x does not converge. Natural log of x diverges, which means that if we take larger and larger values of x, this thing does not approach a particular value. If we had something a little bit different, if we had something like this right here, x would get larger and larger and larger. This would approach 0. And then that would prove convergent. But because we don't have that situation, we just have 1 plus x in the parentheses, this part diverges. So we're not actually able to take the integral of this one. Sometimes, like I said, sometimes you have to get through the integral and tell if this converges or not, but not always. there might be a bit of a shortcut. And I really like this problem because it's a nice segue into our next topic that I want to talk to you guys about real quick. So there is a really easy way to tell if something converges. Sometimes we don't even really need to take the limit. So we want to consider the degree of the numerator, and we want to consider the degree of the denominator. So we can ignore the 1 in the denominator. We can tell that we have basically a degree of 0. Because if we had something like this, let's say we have an invisible x to the 0 power. So anything to the 0 power is 1. It doesn't matter what x value it is, that would always just be 1. So we just have the same old thing we have on top as always, we have 1. So the degree of the numerator is 0. The degree of the denominator is 1. And there is a really useful trick we can use to help us with this. So we have, I'm going to just rewrite this as 1. I'm not going to put x to the 0, x to the first plus 1 downstairs. And then this tells us we have a really important piece of information that will help us tremendously with something like this. So in general, this is something that applies to all integrals. If we have the improper integral going from 1 all the way up to infinity of 1 over x to the p times dx, this converges if and only if p is greater than 1. And it diverges if p is less than or equal to 1. If and only if so for this 1 in the denominator has no effect on it because this 1's not going to change. This part depends on x. This part's going to keep growing. The 1 does not change at all. So we don't even really need to consider the 1 in this particular example. The only thing we really need to consider is the degree of the denominator. So the degree of the denominator we can tell is 1. So in this case, we can tell that p is going to be 1 for this particular problem. So if p is 1, we know this thing diverges. So we took the integral, we made it all the way up to plugging in our endpoints. We could tell it diverges, but we could have also just used this quick test to tell if it converges or diverges. So in this case, the degree of the denominator is 1, so it has to diverge. So I don't know if you guys are taking notes, but I highly recommend you put this in your notes because this one is particularly important. So now we want to talk about something called the comparison test. So the comparison test is really useful in a situation where we have two particular expressions and we have information about one of them. And that information will help us determine convergence and divergence for the other one. So for example, here actually, you know what, before we do an example, I want to just give us a definition of what this is, just give a rigorous definition of the comparison test. Suppose we have two functions, f of x and g of x. Let's suppose that f of x is greater than g of x, greater than or equal to. And let's say g of x is greater than or equal to 0. So we have two situations to consider. Situation A would be if the integral of a to infinity of f of x dx converges, then the integral going from a to infinity of g of x dx also converges. And then there is a second situation to consider. So this time we're going to start with the integral of g of x. So we have if the integral going from a to infinity of g of x dx, if this diverges. Then we also have the fact that the integral of f of x would also diverge. So let's maybe take some particular functions to get a more intuitive sense of what this really means and how we can use this to help us solve problems. So I think maybe Wolfram Alpha or Desmos would be helpful in this situation. Give me a quick second and I will come up with an example to help us understand this a little bit better. All right, I found a pretty good example in my book. So I'm gonna just type this into Desmos and then I'll share my screen momentarily. So let's consider these two functions. Let's consider g of x is equal to 1 plus e to the negative x over x. And then let's consider f of x is equal to just 1 over x. So we can use the comparison test to determine if g of x converges or diverges based on whether f of x converges or diverges. So let's take a look at the graph real quick. So we can see that this function on top is going to be 1 plus e to the negative x over x, and then the one below that is just 1 over x. So we can tell that the one involving e to the negative x is greater than the other one on all positive values of x. If x is positive, then this would be greater than 1 over x. So now we know for sure which one is greater. Now let's go back to the whiteboard. So we know that this function on top is greater. So let's determine if f of x converges or if f of x diverges. So we're going to use the p test that we did in the last one. It's the one that tells us that if we have 1 over x to the p, if p is greater than 1, it converges. If p is less than or equal to 1, it diverges. So in this case, in f of x, we have 1 over x to the first power. So then we know that p is going to be 1. So that means it diverges. So f of x diverges, absolutely. So let's take a look at the information we have. So we know f of x diverges, and we also know that g of x is greater than f of x for all x that is greater than or equal to 0. And I don't know if you guys are familiar with set builder notation. This is just part of set notation. This means for all x. It means that we can pick any x value that's greater than 0, and this would be true. This just means for all. This is true for all x that is greater than or equal to 0. This is true. So g of x is greater than f of x. So I think we can use b to determine definitively if g of x converges or if it diverges. So it tells us that if the smaller of the two functions, it tells us that if the smaller of the two functions diverges, then the other one also diverges. So let's switch letters real quick. I'm sorry, it might be kind of confusing. I want the smaller one to be f of x. So if the smaller function diverges, the bigger function also diverges. So if this f of x diverges, this definition in part B tells us that g of x also diverges. So that's the comparison test. It's pretty handy. Oftentimes we don't have to take a limit. We don't have to look at the graph of something. The comparison test makes it much, much easier to tell if things converge or if they diverge. All right, let's try something else. This time, let's actually apply it to an integral. Let's take the integral going from 2 to infinity of cosine squared of x divided by x squared dx. Our question is, does this converge or does it diverge? So we're going to use the comparison test for this one. So we want to pick two functions, or we want to pick one function that we can compare this to, one that would be either greater than this or less than this. So we know that cosine squared of x is always going to be positive as long as x is greater than 0. Cosine squared of x is greater than 0 for all x values that are greater than 0. So if x is greater than 0, this is absolutely going to be greater than 0. So then let's talk about what we could possibly compare this to. So the denominator, we have x squared. So I think what we could do is we could compare this function with this function right here. We want to determine if one of them is larger than the other. So if we call this function A, we call this function B, knowing that cosine squared of x is going to be positive for all positive values of x, and we know we're only considering positive values of x. So if we look at the integral, we can tell that we're going from 2 all the way up to infinity. We're not including any negative values of x in our integral whatsoever, only positives, which means that both of these are only going to be positive values. We're not going to have any negative function values for any values of x in this particular problem. So I want to hear from you guys in the chat, please. I want you to tell me if you think A is going to be, in general, bigger than B, or if B, in general, is going to be bigger than function A. Which one would have higher function values? I'd like to hear from both of you in the chat, please. All right, thank you for your answer, Lynn. So Hannah, what do you think? Do you think A is going to be bigger in general, or would B be bigger than A? All right, thank you very much. I got answers from both of you guys. You both say B, and you're both correct. So how do we know that? We know B is bigger than A because cosine of x returns function values that are between -1 and +1. And if we square fractional value, so for example, just for the normal value of cosine, they oscillate between -1 and +1. So that means -1/2 is included, -1/3, -1/4, 0, and then +1/2, +1/4, and so on and so forth. So if we square a fractional value, if we square, for example, 1/2, we get a much smaller number. We get 1/4. If we were to square any normal unit fraction like this, we're always going to get a smaller number, which means if we look at function a, we have cosine squared of x on top. It means if we plug in anything except 1 or -1, this is going to be smaller than 1. So that's just a quick way to definitively prove that b is definitely going to be greater than a. Oh, sorry, didn't mean to erase all that. Put that back, okay. We know that b is definitely going to be greater than a. So now let's see if we can make a conclusion about which of them converge and which of them diverge. So we have this one is greater than the cosine squared x over x squared. So, and I want to hear from you guys in the chat one more time. Do you guys think 1 over x squared converges or diverges? And just recall how we figured that out last time. We had p was equal to the degree, and we used that information to tell if this converges or diverges. It depends on the value of the exponent. So I want to hear from both of you in the chat. Do you guys think 1 over x squared converges, or does it diverge? Perfect, exactly right. So we could go back to the definition we had a few minutes ago that tells us that if we have something like this, we can easily tell if it definitively converges if our value of p is greater than 1. So we can clearly see that in 1 over x squared, we have a p-value of 2. So because p is equal to 2 in this case, this tells us definitively that the integral converges. So let's go ahead and write that in. This definitely converges. And I want to hear from you guys again. So based on the fact that 1 over x squared converges, do you guys think the cosine squared of x over x squared is going to converge, or is it going to diverge? So take a look at situation A at the bottom and situation B, and use these facts to determine whether this is going to converge or diverge. Let me know in the chat what you think. All right, thank you, Lynn. So what do you think, Hannah? Do you think it will converge or will it diverge? All right, perfect. Yeah, you both got it correct. It converges. Why does it converge? Well, we know that if a function that's greater out of the two converges, we can use situation A. So f of x converges, then g of x, we know g of x is smaller than f of x. So if a function converges, then a smaller function also converges. And this is also kind of relatable to something we learned in the first few weeks of this class. Remember when we were discussing limits and we talked about something called the squeeze theorem or the sandwich theorem? It is actually loosely based on the squeeze theorem. And this is something we did when we were first learning limits. Limits were something kind of new and foreign to us. So it told us that if we have 3 functions, hang on, I think I can make that a little bit neater. So on and so forth. It tells us that if we have 3 functions, and if one of them is going to be smaller than the other 2 for all positive values of x. So for example, if our bottom function is f of x, middle function is g of x, and then top function is h of x. The squeeze theorem tells us that if f of x and h of x both have limits that exist. Here, I want to rewrite that. So if this limit exists, and if the limit of our top function exists too, oh, I forgot the limit. And limit as x approaches infinity for h of x also exists, then the thing in the middle, g of x, also exists. And they have to also be equal. So if they equal to each other, this is getting messy. Sorry, here, I think I'm just gonna rewrite that. Sorry. So if the top limit equals the bottom limit, then the thing that appears in between them would also be equal to both of them. So I want to maybe show you a better example, a better graphical example. So if we have a function like that, and then we have some other function, and eventually they approach the same value, that means that if we have a separate function between them that stays between them for all values of x, we know that because the top one and the bottom one both eventually reach the same limit, the one in the middle is also going to have to reach the same limit. We know that the blue one is never going to jump above the top function. We know it'll never go below the bottom function. That being said, we know it'll always be equal to whatever these two limits also converge to. That's it. And that's kind of relatable to what we're doing now. We can kind of draw an interesting parallel between this and the other things we've been learning so far. Let's see if I can go back all the way. I've never actually tried this before. I don't know if there's like a limit to how many times we can go back. So definitely let me know in the chat if you have any questions. So far, we have reviewed convergence. We have reviewed divergence. We've done the p-test. We've done the comparison test. We've learned lots of new things about convergence of definite integrals. So tell me if you guys have any questions about anything whatsoever, and we can go over anything you want. And if you don't have questions, I guess we could just continue doing some examples. We might have time for a few more. All right. Let's try something different. Let's say we have the integral going from 3 to infinity of 1 over x plus e to the x dx. And we want to determine if it converges or diverges. So we're going to use the comparison test. So we want to be really strategic about what function we pick to compare this one to. Do you guys have any suggestions? I want to hear from you guys in the chat. I want you guys to maybe suggest a function we can compare this one to, namely a function that we know definitively converges or definitively diverges that we can use to help us determine whether this one converges or diverges to. See if you can come up with a function to compare this one to, please. And then send me your answers in the chat. So we don't have much time, so I think I'm just going to pick something myself. So I want to pick 1 over x. And we know 1 over x diverges because this is x to the p power. P is equal to 1. And whenever p is less than or equal to 1, it diverges. So this diverges. So we want to tell which of these two functions would be bigger. So we can tell as x approaches infinity, what we have here on the bottom would get actually smaller because the x part of e to the x, as x approaches infinity, this would actually just keep going on and on forever as well. And then same thing with x. So this would grow at a much larger rate than 1 over x because this adds a significant amount to the function value as x tends to infinity. So we know that this one is greater than that. So unfortunately, we can't use any of these. We know we have two functions. The greater one diverges. Now, if the smaller one diverged, we would have we'd have a lot more information. But the fact that the bigger of the two diverges tells us nothing. So on my part, this was a pretty poor choice for a comparison function. Doesn't give us any information. So let's maybe pick a different one. Maybe instead of 1 over x, maybe we could pick 1 over e to the x. There's no guarantee this one will work either, but it's definitely worth a shot. 1 over e to the x. So let's see if we can determine which of these would be bigger. So this one on the left, as x tends to infinity, this would add a considerable amount. This one has the plus x, the one on the right does not have the plus x, and that's the only difference. So as x gets increasingly larger, this denominator would get increasingly larger than this denominator. They would grow more and more separate as x increases. This one would just get smaller over time than this one, much smaller than the one on the right. So this one we know would, does 1 over e to the x converge or does it diverge? This one, I believe, would converge because as we take larger and larger x values, this would just approach 0. So we have a bigger function and we have a smaller function. So we know that because the bigger function converges, the smaller function also converges then. We can use situation A in this definition. So f of x converges, then g of x also converges. So we don't have enough time to integrate, but that's perfectly okay. That's not really the main goal of this topic. Our goal is just to determine convergence and divergence. So a quick recap, this converges, so the smaller function also converges. All right, so this is a lot of new information. It seems kind of weird and foreign because we've been studying integrals, we've been studying derivatives. It's pretty clear how those two are related to each other. And right away, it may not be perfectly clear how series and sequences are related to these things, but as we do more in this section, it'll become more and more clear why this is important to learn in calculus. So it's a lot of information, a lot of new information to take in. So I recommend you guys study and read up on this over the weekend. Just give yourselves a bit of a refresher so then when the time comes when we have class on Sunday, you guys will be really comfortable with this material and we'll be able to start infinite series. All right, well, I hope you guys have a wonderful weekend, and I will see you next time.